This is R.D. Sharma, Solutions, Chapter 3, Binary Operations, Exercise is 3.1. This is from class number 12, and this chapter 3 can be in your book because there are different editions. It can be chapter 4. The question also may be jumbled up. My question 3 can be your question number 7. So before we go ahead, let me tell you certain thing that the questions I will not be able to show because of the copyright issue with R.D. Sharma book. There will be a problem because I already faced it. And the answer here is why I have shown you the answer, because in your book or sometimes in your tuition, etc., coaching classes, you have to write exactly how you need to write. My idea is to tell you the logic, the reason behind why we are doing and how to solve a question, right? So let us start with the first question of the exercise 3.1. That is, determine whether each of the following operations define a binary operation on the given set or not. So let me tell you about a binary operation first. Any binary operation will represent it by star or O, or you'll see multiple symbols just now. So we have actually taken all these symbols plus, minus, into, divide, and we have just used a single symbol. The binary operation is all about the star, which is such that the two values, that is the two values will be taken from the set, and the result will be also belonging to the same set. Okay, so this is the binary operation. The basic is the two values which are operating should give you the result in the same set. So the first part of this question is star on n. So we are talking about star, which is our binary operation, on the set, because every time we need to have a set. So this set is a natural number defined by A cross B or A star B equals A raised to power B, that is the exponential function, for all A comma B belongs to n. So this A, B are belonging to n, that is, we are talking about a natural number set. Now it is in your hand if you want to show it like this, which in the solution you are seeing, or you can also solve it using an example. That is, if you are able to show in either way, you can do it. So what is the natural number? The different sets. So natural number is a set of counting numbers. 0 will never be there in the natural number. It will be 1, 2, 3 till the infinity on the positive side. There are no negative numbers. There is no 0. So what we are saying, whenever we do these kind of questions, we'll always start that this A and B, that is the by two values which are operating together, should belong to a certain set, and we are taking a natural number set. So this A and B are from natural number set, and when they are operated, the result should also be in the same set, and that will tell you that it is a binary operation. So same thing we are going to do here, and we'll take an example also. You can show it using an example. Now take any value from this natural number set A, take any value from this natural number set B. This is the exponential function, A to the power B or B to the power A. All these are exponential functions because A and B, B and B, you can always change, and they are coming from the same set. So say 1 and 3 we are taking. So 3 to the power 1 or 1 to the power 3, or say 5 or 2 you take, 5 to the power 2, 2 to the power 5. So 3 to the power 1 is 3, 1 to the power 3 is 1, 5 to the power 2 is 5 is 25, and 2 to the power 4, 16, it's 32. Okay. So you have these values. Okay. Now these are all natural number. So A to the power B, whenever you use A and B from natural number, A to the power B also goes to the natural number, and that is the basis of any binary operation. Okay. So for other question also, let me remind you, you have to tell that A and B we are taking from that certain set, and we'll try to define that this operation value or operated value or the final value should also go to the same set, and that will be a binary operation. The next one is now the symbol has been changed here. The symbol which we were using star has changed to O or 0 whatever you need to call it. So this is on Z, and now this set has changed. Previously it was the natural number, now it is an integer. And it is defined by A operation B equals A raised B for all A comma B belongs to Z. Now if you see, the first part and second part means the previous and this one are exactly same. The only difference is the set we are taking. The previous question, the set was a natural number. Here the set is the integer. So we will be taking 0, we will be taking negative numbers also. It's all about sets. So same thing we are doing, trying to depict whether it is possible if you take A and B from the same set and the result is also going to the same set. So Z is all about the 0, -1, +1, -2 and +2, -3, +3 like this. And this ellipsis, 3 dots, these 3 dots means it goes up to infinity. It goes up to till the time we stop. Okay, so now this is the Z. When you say Z plus, that is on the right hand side, 0 till infinity, or you say Z minus, then you start from -1 till infinity, -infinity. So A operation B is A raised to the power B, and as I said, the best way is to take a value. So first we have to say that we are taking the value A from the set Z. B also we are taking from the same set, that is the integer. So both of the values we have taken, and we have to prove A to the power B belongs to the same set Z, then it is a binary operation, otherwise not. So as I said, we can take the example. So you can take any two values, and the best values are those values being chosen which in the first attempt shows that it doesn't belong to Z. So I'm taking A as a 3 and B as a -1. So A as 3 and B as -1, what do we get? We get A raised to the power B as what? Because that number surely doesn't belong to Z, because 3 raised to the power -1 is eventually equal to 1 by 3, and 1 by 3 is what? Is 0.33 something. Let me just show you here. So it will be 0.33, but the 0.33 is not belonging to that Z. And as I said, in binary operation, we always need to have A and B from the set, and we have to prove that when they are operated, it belongs to the same set, and it is not belonging, because 0.33 is actually a real number which is not coming in the Z, that is Z or integer. So this particular question, because you can safely say that it is not a binary operation. O or 0 is not a binary operation, because A and Z belonging to Z, but the A to the power B in this case is not belonging to that set. The third one is star. Again, we are coming back to the natural number. So star on n defined by, now here we have a proper expression for A star B. So A star B is equal to what? It is equal to, when A and B are operated, it is going to give you A plus B minus 2 for all A and B belonging to n. So we are talking about natural number. A and B are belonging to natural number, and this natural number is always a set of counting numbers. So we don't have a 0, we don't have any negative number here. We start with 1 and goes up to infinity. So 1, 2, 3 like this. Okay, this is the natural number, and earlier I said whenever we take this A and B, we have to take from this set, and then A belongs to natural number, so we assumed A and B are belonging to this natural number, and the result should also go to natural number in order to prove that it is a binary operation, otherwise not. So A is equal to 1, let us assume A is equal to 1, B also equals to 1. Why I have chosen this number, you will just see in a bit. Because when A and B are chosen as 1, A star B is defined as A plus B minus 2. So A and B. A plus B minus 2, A is 1, B is taken as 1 and minus 2. So what do you get? 2 minus 2 is a 0. What do you get? A 0, which is not a part of a natural number. When it is not a part of natural number, of course, this binary operation is not defined on the natural number n. Okay. 1 plus 1 minus 2 is 0, and 0 is never in a natural number. 0 is not a counting number. So this star is not a binary operation on the natural number set. Okay. Now in this part, the symbol, or we can say the operation, we can use star O, and here it is being given x6. 6 is subscript. But you can take any of them. The basic idea is that if A and B belongs to that set, the result also should belong to that set. The only baseline is that. If you can just understand this line, binary operation is clear to you. Okay, coming to the symbol back again, we have a set also given. So x6 is the operation symbol. The set is given by 1, 2, 3, 4, 5. So this is a kind of restricted set, you can say, that you don't have an open-ended set like natural number and the Z. So we have 1, 2, 3, 4, 5. And the operation is given like this. AX6B is defined what? It is defined by a sentence. The sentence is remainder when AB is divided by 6. What does it mean? I'm writing in short. So remainder when AB is divided by B. AB, that is A cross B, A multiplied by B. This is divided by 6. So whenever the operation is applied, you have to take A and B multiplication, and then you have to divide it by 6. Whatever value is there, that is the result. And in order to prove this as a binary relation, that result should be in S. 1, 2, 3, 4, 5. The resultant should always be among 1, 2, 3, 4, 5. Otherwise, it will not be a binary operation. Okay. So we'll try to prove it. This A cross B by 6, that is eventually what we are going to do on the right hand side. Here, I can see that there are certain values which are not in the set, 0. Okay. But I'll just discuss it later. First, let us take a certain value and try to show that what you're getting. Okay. There is another question which is coming next, which is the 5th question. It has almost the same flavor, but let us complete this one first. So we are actually making a binary operation table here. This binary operation table, every value is operated with every other value of the set, and then you get the final value, which is AX6B, which is the remainder when A into B is divided by 6. Okay, we'll take a random value, 2 values, and that is enough to prove that whether it is a binary operation or not. So I'm taking A as 2 and B as 3. Remember, A and B has to belong to that set. So AX6B is what? 3 into 2 divided by 6, because the remainder when A and B is divided by 6. So 3 into 2 divided by 6, 6 by 6, the remainder is 0. There is nothing left when you divide it. So what do you get? AX6B is 0. Is 0 belonging to the set? No. As I said, the operation value should always belong to the same set. It is not. So very clear that this x6 is not a binary operation on this set. For example, 1, 1 operation, you take 1 into 1 divided by 6. What do you get? 2 by this 1 by 6. So 1 is the remainder. This is how you build this composition table, or you can say a binary operation table. It's always easy to make a binary operation table. It is so that you can easily see that these numbers, the operated value numbers, whether all these values belong to this set. I'm just marking that area where you have to see these all values should belong to that set 1, 2, 3, 4, 5, 6. But it is so easy that this S as 1, 2, 3, 4, 5 on the row and the column we have written, and we can easily correspond to A into B divided by 6, and we see that there are certain outliers. What are the outliers? 0, 0, 0, 0. This 0 is not belonging to this set. So when you have an operation and that value which is coming out of the operation and it is not belonging to that set, we can easily say that this is not a binary operation on this particular set S. So x6 is not a binary operation on set S. Now the next one is again here we have plus 6, not x6. So let us write it as plus 6 or x6. It's just a symbol, so it doesn't matter. I'm just writing it as like this. Okay. So we have this plus 6 on as the set is, see, previous it was 1, 2, 3, 4, 5. Here 0 is also included. And it is defined by, there is a proper mathematical interpretation for this, that when you operate A with B with plus 6, what do you get? If you add A and B, and if it happens to be less than 6, then the value will be A plus B. But if you add A plus B and it happens to be greater than or equal to 6, then you have the value A plus B minus 6, right? So take the set and this operation. I'll just tell you 1 or 2 values and you'll be able to know how we make the composition table. We have to write these all value in the row 0, 1, 2, 3, 5, 4, 5, 6. No, there is no 6. Oh, I'll just cut it. Then we have 0, 1, 2, 3, 4, 5. Again 6, I'm going to cut it. So don't bother. A plus B. See, A plus B. A should always be taken from the first column, you can say. And the B should be taken from the first row. So I'm taking A as 2. I'm just trying to show that A plus B is less than 6. So B I'm taking 3. So A and 2, A and B, just add them, you get A plus B as 5. 5 is less than 6. Okay. I purposefully took A and B so that it is less than 6. So 5, 2 plus 3 is 5. So it is less than 6. So this is 2 I have taken from here. And this is 2 I have taken from the first column. The first row I have taken as 3. So you get 5. So this is how this 5 has come. I hope you will be able to do all the other values. Let us take one more value in order to prove the second part, or to just depict the second part. I just said that 6 has to be cancelled because it is not there in the set. So what we take the highest value so that we go beyond 6. So A I am taking as 5, B as 5 because I know A plus B is going to be 10, which is greater than or equal to 6. So the second condition will be fulfilled. So when this A plus B is greater than or equal to 6, what we have to do, A plus B minus 6 will be the value. So this is where I am going to put the value. A plus B minus 6, which is 5 plus 5, that is 10, minus 6, which is eventually 4. So this 5 and this 5 is going to give you, this A I have taken from the first column, B I have taken from the first row, and this 5 and 5 gives me a 4. So this table also, the 2 value I have shown, so you can make all the table, and this value is 4. Now if you see that when we make all this table, see, our answer is fixed. We have already shown you the answer. But this box which I am showing, all the values should belong to this set S. And can you tell me any number which is outlier? No. There are all the numbers which are there, so it is a binary operation. Now the next part is, the symbol is somewhat different, which is a circle. Inside this we have a dot. So this is a symbol, and this is on n. N is the natural number, and this is defined by a operation B is equal to a to the power b plus b to the power a for all a and b belonging to the natural number. So a and b should belong to natural number. Then we will prove a to the power b plus b to the power a. Whether it is belonging to a natural number, it is a binary operation. It is not belonging to a natural number, this natural number set, it is not a binary operation. So n is, see, n is, as I told you, you can always take an example. But since the first part, which we have already discussed, a to the power b, b to the power a, they are actually the natural numbers. So a to the power b, a belonging to a natural number, b belonging to a natural number. So a to the power b is a natural number, which we have already discussed in the first part. You can use any value out of it, and you can prove it also, as I proved in the first part. Similarly, b to the power a, b is a natural number, a is a natural number, b to the power a is simply the exponential function. So you can always prove that it is also a natural number. So when you add two natural numbers, it is, but natural. We have already seen in the earlier classes, adding two natural numbers will always give you a natural number only. So finally, we get a natural number. So this operation, this whichever symbol is there, is a binary operation on this natural number n. I hope you got the idea. If you are not able to understand, just revisit the first part, and then you'll be able to comprehend it more. Now, seventh is, see, the star. Again, we have come back to star on Q. And now this Q is a rational number. A rational number is always of the form of P by Q. Rather than depicting it by A by B, we will always try to depict it by P by Q form. So this star is on Q, and this is defined by, when we operate A and B, you should get a value, or the final expression is A minus B divided by B plus 1. And this is for all A and B that is belonging to Q, which is ultimately our rational number set. Okay, so what we have to do is, we will say that A belongs to Q, we will also say B belongs to Q, and then if A minus B by B plus 1 belongs to Q, that is a binary operation. If it doesn't belong to Q, that is not a binary operation. So A is 2, I'm just taking A as 2, and B also as -1. Why? A is 2 because 2 to the power 2 by 1. You can write 2 is 2 by 1, which is of the form P by Q. So every number here, what I'm taking is a rational number. So B is equal to -1. -1 also you can write -1 by 1, which is also of the form of P by Q. So it is also coming from the Q set, which is the rational number. Okay, when we take 2 and -1, because they both are coming from Q. So whether this A minus 1 by B plus 1, whether it is coming from the actual Q or not, that we have to see. So 2 minus 1 divided by B plus 1, -1 I have taken, -1 plus 1. So this, we have done it purposefully actually, knowingly, because the denominator, if you see, is going to be an undefined number. The number, if I give you 3 chocolates and I say divide it in 3 parts, you will divide it. If I say you divide it into 0 parts, you'll say, oh, what is this question? I cannot. Nobody can. How can you divide something in 0 parts? No parts. So 1 by 0 is an undefined number, and this undefined is in no set, let alone the Q set. It is not in Z, it is not in natural number, it is not in any other set. So this is not a binary operation. So let me write it. This is not, I have to write, it is not a binary operation on Q. Okay, you got the point? Okay, this question we are going to take in the next discussion. Thank you so much. Take care of yourself.